All right, so section 10.2, we're going to continue on with sequences, and specifically, we're going to talk about limits of sequences. We will return to the idea of series and adding things up in the next section and then throughout really the rest of the chapter. But for now, yeah, limits of sequences is what we're after. And really the main goal here, there's a couple of things. The focus is limits of sequences and how to compute them. Okay. Now the key thing, really the biggest key thing is this theorem right here on the very first slide. I put it here. Basically says if you know how to take limits of functions, then you're pretty good with limits of sequences. Okay. So let me just make a few kind of basic observations here. So basically, something like the limit as x goes to infinity of 1 over x is equal to 0, right? This is a fact that we use an awful lot already in Calculus 1. That's really the same as saying the limit as n goes to infinity of 1 over n equals 0. So known facts about functions turn into known facts about sequences, all right? Some other facts that end up being pretty important. The limit as x goes to infinity of, let's say, like 1/2 to the x power. Well, that's going to be equal to 0, okay? If you take a number that's less than 1, you raise it to larger and larger positive powers, the fraction just decays down to 0. That's the same as saying the limit as n goes to infinity of 1/2 to the nth power is equal to 0, okay? And then even things about uh, limits being infinite, right? So if I said the limit is as x goes to infinity of e to the x, well, that's infinity. Okay. Well, that's the same as saying the limit as n goes to infinity of e to the n is equal to infinity. Okay. So point is, yeah, if I know certain limit computing facts for functions, they turn into things about sequences. Um, let's see how a couple of things play out. So the limit laws for sequences, well, they're the same as the limit laws for functions because those limit laws held for functions, and because when facts hold for functions, then they hold for sequences, you end up with all the same limit laws that we had before. Okay, that's great. Here, let's add a fifth one on here. Okay, so if I suppose that the limit, oh, okay, so we're supposing that an converges to capital A and the bn's converge to capital B. If I suppose that let's say G is continuous at capital A, then the limit as n goes to infinity of g of an, it just ends up being g of a. Basically, you can push the limit inside of a continuous function, provided that the limit exists. All right, so let's use these limit laws and do some kind of review problems to see how we can apply what we know about limits of functions to limits of sequences. And we're just going to do a couple of these. I'm going to do A and B. I don't want to do C because it's like very much like B. But the main thing is this. If you look at some earlier sections in our book, I believe that they were section, yeah, 2.5 add limits to infinity. And then our section on L'Hopital's rule, which I think was 4.7 or 9. Oh no, 4.7 or 4.9, whichever one of those is L'Hopital's rule. These are two really important sections to go back and review to think about limits of sequences because they're just limits of functions at infinity. Everything applies directly. So just to show, look, instead of thinking about this sequence for part A, if you think about the function f of x equals 3x cubed over x cubed plus 1, and then you want to consider the limit as x goes to infinity. Well, we've already dealt with this in a couple of different ways. You could use L'Hopital's rule because it looks like infinity over infinity, or you could divide out by the fastest growing term in the bottom, which is x cubed. So I'm going to take it that way. The limit as x goes to infinity of if I multiply top and bottom by 1 over x cubed, okay, then this ends up looking like 3 on top, 1 plus 1 over x cubed on the bottom. And now I apply the limit laws here. 3 on the top, 1 plus 0 on the bottom. Answer is 3. So because I can compute the limit for that function, this sequence, when you just switch to n's, the limit as n goes to infinity, 3n cubed over n cubed plus 1, it's also 3. Okay? So the method that I just kind of used there, you can go back and look at section 2.5, and there's lots more examples that are similar. Okay? Um, for part B, let's look at B. If you just try to kind of use intuition, what happens? Well, on the inside here, if I think about this like x plus 5 over x, the inside's going to 1, but the exponent is going to infinity, right? And so, look, part B has this kind of 1 to infinity indeterminate form, okay? So review the L'Hopital's rule section. You've got these indeterminate forms. How do we deal with something like that? Well, you can basically, again, just kind of, I'm going to think of it as f of x equals x plus 5 over x to the x power, okay? It's 1 to the infinity. Now, what can we do? We can use L'Hopital's rule. Remember, there's a little bit of a trick to this. You basically are going to do e to the natural log of your function, okay? E to the natural log of my function. What happens here is I can use a property of natural logs to pull that x out front. So x times natural log, x plus 5 over x, okay? Now what's happening here, as x gets larger and larger, the x factor goes to infinity. The inside here goes to the natural log of 1 is 0. So up in the exponent, this has now kind of the form, just up in the exponent, it looks like 0 times infinity, something like that, okay? So when you have one of these, the first thing you want to do is make sure you're using rules for logarithms, okay? The next thing I'm going to do is take the limit just up here in the exponent, and then third thing I'm going to do is take that result and put the answer together, okay? So I'm going to compute the limit as x goes to infinity of, x times the natural log of, and I'm actually going to take on the inside piece here, I'm going to rewrite this as 1 plus 5x to the minus 1. So I just kind of split that up, okay? And so again, this has the infinity times 0 thing to it. So to use L'Hopital's rule, I need to force this into a fraction. So what I'm going to do in this case is I'm going to say, I'm going to leave the natural log factor on top, okay? And then on the bottom, I'm going to write 1 over x. So x to the minus 1 goes to the bottom, okay? Now I can hit this with L'Hopital's rule because at this point now this looks like 0 over 0, okay? So I can use L'Hopital's rule at that point because I have a fraction, 0 going, tendency to 0 on top, tendency to 0 on the bottom, and we're just going to differentiate. So on the top here, the derivative is 1 over the argument, so 1 over 1 plus 5x to the minus 1, times the derivative of the argument, so negative 5x to the minus 2, okay? On the bottom, the derivative is what? Well, let's see. You're going to have a minus 1 times x to the minus 2. So what ends up happening here is you get cancellation. The minus sign cancels here, and the x to the minus 2's cancel, all right? And now you can actually just take the limit using limit laws. It's a positive 5 now because the minus canceled that off, and you have 1 times 5. The answer is just 5, okay? Now, remember what that is here is the limit of what's going on in the exponent, okay? So now we can kind of use that continuity property and say the following thing. So the limit of what we wanted, so the limit as x goes to infinity of the f of x function is equal to the limit as x goes to infinity of this, e to the natural log of f of x, okay? And that's equal to what? Well, I know that the exponent part here goes to L. So that's e to the L, which is e to the 5th power. All right, so I just did one of those weird exponential indeterminate forms. And all this just looked like function stuff. The point is, if I can do it for functions, then a similar thing holds for limits, okay? So the limit as n goes to infinity of this Bn sequence is the same answer, e to the fifth, okay? All right. And again, part C here looks very much like part B. All right. Now, there are some new things about that we're going to start talking about. Like the thing is that with sequences, we could spend an awful lot of time on this. And so we're doing in calculus, remember, it's a computing class, right? Um, it's a computing class. The backbone, the foundation for it is mathematical analysis. And so in math analysis, sequences are really, really important because it helps us build the logic of why calculus works together, okay? So it turns out there's a lot more that we could talk about that we're not going to, because it doesn't all relate directly to computation, but it is very important background knowledge. Let me see here. I think what I'm going to do, let's just do this. I'm just going to say a little bit about terminology because these do end up being important. But let me just point out the following thing. Increasing, non-decreasing, decreasing, non-increasing, monotonic. All these first five things, they relate very much to just increasing, decreasing, definitions that you saw at the beginning of chapter 4. Okay. So this would have been at like section, if you look back at section 4.2, we talked about increasing and decreasing functions. And you know how to test and see if f of x is increasing or decreasing. You can take its derivative and see whether the derivative is positive or negative, right? Well, the same thing kind of works for sequences. If you have a sequence an and it corresponds to a function f of x, basically just replace the n's with x's. If you can do that, you can analyze the sequence being increasing or decreasing by taking the derivative of the function, okay, and then seeing if it's always positive. If it's always positive, then it's increasing. If it's always negative, then it's decreasing. If it's greater than or equal to zero, we can say it's non-decreasing, and less than or equal to zero, we can say it's non-increasing. Monotonic is one or the other. Okay. So I'm not going to worry too much about that for now. It will come into play in some of our testing stuff later. So I just wanted to prime the terminology. Another fact that we could talk about, we're probably not going to need it too much, just has to do with bounded sequences. Now, a bounded sequence is one that basically has a number that's always larger than all the sequence values. It has to be bounded above. Bounded below just means the opposite, right? There's a number that's less than or equal to all of the sequence values, okay? And again, that will come into play in some of our testing, okay? So we'll talk more about it. I just wanted to introduce the notation, okay? Now, again, sequences are a little bit different than the calculus functions that we've seen so far. And in particular, one of the things is this -1 to the nth power. We never saw -1 to the x, by the way. You never saw f of x equals -1 to the x. Why? Well, because the domain of this function is awful. All right. This function doesn't make any sense whenever x is an irrational number or even a lot of fraction numbers. Okay. We don't talk about this function because it's not a nice, it doesn't have a nice domain, and that the domain doesn't have like nice intervals. Okay. It has all these gaps and holes. This is not a good continuous calculus function. Okay. But -1 to the n for integer powers totally makes sense. And it actually shows up a lot, again, in some of our examples. So what ends up happening here is that it gives us this alternating up and down kind of behavior. And so here's just a quick image of what this b function looks like, okay? When the n is an even number, right? -1 to the n is just an even factor. And so you end up with all positive terms up here because the rest of the factors are positive, okay? And when n is negative, or sorry, when n is odd, -1 to the n is a negative factor, makes this whole fraction negative, and they go down here, okay? So what you can kind of see is that this function bn, it back and forth between above and below, right? But these ones go towards 1, these ones go towards -1, and so we have a divergent, this one's divergent. Okay, goes back and forth, up and down. Part A here, we can analyze just like we did before. Okay, the limit as x goes to infinity of x to the 3 halves divided by x to the 3 halves plus 1. Well, top and bottom have like the same growth, I want to say like the same kind of growth factor, x to the 3 halves. Okay, so if you multiply top and bottom by 1 over x to the 3 halves, this is the limit as x goes to infinity of 1 over 1 plus 1 over x to the 3 halves. Right? As x goes to infinity, this fraction goes to 0 from the denominator. So it's 1 over 1 plus 0. The answer is just 1 for part A. Okay? Which is, by the way, would just be this with all these terms filled in towards the top. Okay? All right. Couple more things. Geometric sequences that they're going to call them, but just a quick review. Here's some really important sequences to remember. And I did this even on the very first slide, just to kind of remind us, look, the limit as n goes to infinity of like 2 to the nth power. Well, that grows really fast. When the base of your exponential is larger than 1, this thing is going to, in our case, go to plus infinity. Or how about just does not exist? Does not exist basically means it could be infinity, could be minus infinity, could be what we called does not exist before. Any of them just float into that. Does not exist as a number, okay? If the base is too large, it doesn't exist as a number, right? Similarly, if you look at the limit as n goes to infinity of negative 3 to the nth power, well, that just does not exist, okay? It's the values get large, okay? Large positives mixed with large negatives, bouncing back and forth, but they're not honing in on a value, right? Versus things like the limit as n goes to infinity of 1/2 to the nth power, right? If you do powers of a half, we got a half, a fourth, an eighth, a 16th, a 32, a 64th, and so on. This is going to 0, okay? And if you went for like negative 1/3 to the n, well, that's negative 1/3, 1/9, negative 1/27, 1 over 181, right? Negative 1 over 243. So it's like it's still going to 0 in size. They're going from plus to minus, but they're still going to 0 in size. Okay. And so this is just a quick summary of all that information. Again, just for kind of, they're calling them geometric sequences, but how about this? It's exponential functions. As x goes to infinity. That's kind of the intuition that you should think. Exponential functions as x goes to infinity. If the base is larger than 1, then you get blow up, doesn't exist. If the base is between 0 and 1 in size, you get 0. That's all that says. And if the base is 1, it's the most boring thing in the world because it's just 1, 1, 1, 1, 1 also. All right. Two more quick things. I don't have too much more. I'm going to do a squeeze theorem example. Yeah, we got a couple more things. So squeeze theorem example, look, the squeeze theorem for functions and the squeeze theorem for sequences they're really one and the same, okay? And the basic idea of the squeeze theorem, so let's focus on this for a second. The basic idea of the squeeze theorem is you have this function that you want to understand, okay? Bn. Okay? So what we want to do is we want to show that the limit as n goes to infinity of Bn is equal to some limit L. Okay? We have evidence that the limit of a sequence is equal to L. The squeeze theorem is something that you can use to justify that that limit is actually equal to L. Okay? And the way that you do that is you have to come up with a lower bound and an upper bound such that those lower and upper bounds also converge to L. Right? Because like basically you've got something like this, okay? If you were to look at Bn, right, you might have this is like y equals L, okay? And your Bn might look something like, I don't know, something like this. Bouncing back and forth. Something like that, okay? And what we're supposed to be doing is, if you can find something that's above it, greater than or equal to really, all the time, and that's also going to L, and something below it, like this maybe, it's also going to L, right? The pink one is the upper bound, the blue one is the lower bound. Then the black dots in the middle also have to go towards L. That's the idea for the squeeze term, okay? And so we often use this with things like oscillating sequences like this one, okay? And so the cosine part here is just going to have what? Basically, it's going to have the numerator is kind of ugly. It's these numbers that are bouncing back and forth between -1 and 1 kind of sporadically. They're not, it's not in pi, it's just numbers between -1 and 1. And the bottom is nicely behaved, right? As n goes to infinity, the bottom gets huge, the top is bounded, okay? And so here's how you can do, here's what I think, okay? The idea is I have to think top is bounded, like, right? You have bounded divided by unbounded. The bottom is getting huge, right? And this should go to 0. That's my thinking, okay? This needs to be a starting place, is I have to think I know what's happening here. The limit as n goes to infinity of Bn is equal to 0. It's almost like this is a claim, okay? And I need to justify my claim. That's what the squeeze theorem is used for. It's not used to compute something. It's once I have a claim, it allows me to justify it. It has to start together, okay? Now, if you dig that, then what you have to do is you have to come up with the lower and upper bounds that also converge to 0, okay? And here's how we're going to do that. Look, cosine and sine are bounded between -1 and 1, okay? So how about this? We're all in. -1 is less than or equal to cosine, and is less than or equal to 1. We know that for sure, okay? So, how about -1 over n squared plus 1 is less than or equal to cosine n over n squared plus 1 is less than or equal to 1 for all n, right? Oops, 1 over n squared plus 1, excuse me. You divide all three sides of the inequality by the same positive number. It doesn't change the directions or anything. So now I have a lower bound that's nicely behaved, an upper bound that's nicely behaved. They both go towards 0. So since the limit as n goes to infinity of the lower sequence is equal to 0, and that's the same as the limit as n goes to infinity of the upper bound. We know the limit as n goes to infinity of the sequence that we wanted, the thing in the middle, also has to be 0, okay? By the squeeze theorem. So that's what the squeeze theorem is again used for. It's used to make arguments. I need to use it, like usually it's more like this. Teacher needs to use this as a device to show you that things work later. So we study it a little bit. It's a really good analytic tool because it has to do with argument making more so than computing. Okay. Another piece of analytic thing that's also good for argument making that I will not use much in this class, but it's another really important thing about sequences. Bounded monotonic sequences converge. Bounded monotonic sequences converge. What that basically means is that if you have a sequence that has like an upper bound to it, right? Like the sequence is never going to go up above that line, but the sequence is always increasing, okay? It's always increasing, but it never goes up above a line. That means that they must level out to some value. It doesn't have to be the bound, that one upper bound right there. It could be a bound like right here, for example. But if I know it's bounded above, I know it's increasing, it has to approach a limiting value somewhere, okay? These are both really important analytic tool thoughts, okay? All right. The last useful thing I think that we're going to need right now is growth rates for sequences. Look, what ends up what when we look at limits of sequences, as you go further and further, what we end up seeing is that some sequences just grow a lot faster than other ones. Okay, and that's what this is trying to say. Basically, looking at it this way, if you have, what does it say? Positive real numbers P, Q, R, S would be base greater than 1. Okay. What do I know? Well, I'm going to start right here. base greater than 1. This is exponential growth. That's where that sits right here in this hierarchy of how fast things grow. Exponential growth is pretty quick, okay? Basically, it's larger than any polynomial power, okay? It's like polynomial power, okay? This is a greater polynomial. So basically, exponential growth is faster than polynomial growth. That's something that we've had before. What about a new thing here? So we're going to work with factorials more frequently in this class. Factorial growth is much larger than exponential growth. And if you want to know what factorial means, again, it's n factorial. It's 1 times 2 times 3 times all the way up to n, okay? So that's something like 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. That ends up being a pretty big number. 7, what was it? 25, 120 times 6, 700 times, something like that. Anyways, it grows fast. That's the idea. Faster than exponential growth. What's this n to the n power? Well, n to the n power, that's kind of ridiculous fast, because if you think about like 6 to the 6th, well, that's 6 times 6, 6 times, right? Pretty clearly, these bases are all like the bigger than or equal to all of these ones. So this base and exponent moving, exponential and base moving is faster than the factorial. Here's our little theorem. So this is a result that we can apply. Basically, it says that if one of these is before the other one, okay, so appears before B, then the limit of the ratios of A to B is going to be 0, and then vice versa. The limit of B over A is going to be infinity, okay? So let's apply that really quickly here. So natural log of n to the 10th divided by 0.00001 times n. What happens there? Well, technically they both go to infinity. Top and bottom do. Okay, they both go to infinity. But here's what I know. The bottom here, bottom versus the top. So 0.00001 n. That is like this n raised to a power p. Okay, so it's right here, the second one. What's this one? The natural log of n to the 10th power. Well, actually, that's 10 times the natural log of n. So that's just like the natural log q to the n. Okay? The very, very first one. Okay. So because the bottom is faster than the top, what I know is that the limit here the bottom grows much faster than the top. Okay. That means that this limit has to be 0. The bottom is growing much faster than the top. That's what we're kind of going for here. And so let's look at one more of these. Let's look at this one here. Okay, let's look at B. So for part B, you got n to the 8th natural log of n versus n to the 8.001. Okay, so look at this. The power on the bottom is just a little bit more than the power on the top. Okay, there's a couple of ways to handle this. You could actually just simplify what the fraction looks like, which I would be inclined to do. I would actually be inclined to, so it's the top versus the bottom. You could actually just take this and say this is natural log of n divided by n to the 0.001. Okay, if I do that, I can now look at that and say, well, now I'm in the same situation as before, right? The top is a natural log. The bottom is n raised to any positive power, okay? Therefore, slow on top, fast on bottom. So the limit as n goes to infinity of the slower on the top, the faster on the bottom is equal to 0, just like part of it, okay? Real quickly for part C, factorial over exponential. Factorial over exponential. If I look at this list, factorial was to the right of exponential. What that means is that for part C, you have fast over slower, okay? So for part C, your limit as n goes to infinity of n factorial over 10 to the nth power is going to be infinity, okay? The top outgrows the bottom. This is going to be an unbounded fraction, right? And you would see that if you started to just plug in large numbers for this. N factorial grows so fast, and exponentials do too, but if you just tried to plug in something like n equals 10, you'd already see this fraction's getting huge. Plug in 12, it gets larger. Plug in 15, larger stuff. It's going to be unbounded. Huh? All right. So a lot of that was the really the bulk of things that you should kind of think of for 10.2. Number one, it should be about reviewing limits at infinity, using what you already know about functions, using what we already know about L'Hopital's rule, which we've already covered a little bit in this course. Those are important things because I can use what I know about limits of functions for limits of sequences. Okay. Some new things. Well, this growth rates of sequences is handy. It'll be handy for those of you that need to do algorithm analysis someday in a discrete math class, perhaps. This is something that's new and sequence specific. The terminology is a little bit important. I did want to just review it and just say, hey, a little bit about it when it comes to the monotonicity, increasing, decreasing. It's very, very similar to what it was for functions. Okay. Now, lastly, the last thing I'm going to point out, I was thinking about starting off with this, but the definition of the limit of a sequence, I mean, really what's happening here is something like this. We want to say that the limit of a sequence is a number. What is supposed to happen? Well, the sequence values, the ANs, are supposed to be getting closer and closer to some limit L, right? So visually, kind of what that would look like is if you prescribe any threshold, which is what the epsilon is supposed to be, then what ends up happening is something like this picture. If you provide a threshold, epsilon, I can tell you how far out you have to go into the sequence from when all of the sequence values will be within that threshold forever after. Okay? It can't bounce out after that. That's what it means for the limit to be L, is if you provide any threshold, we can find a place in the domain where if you go past that, you're going to be within the threshold guaranteed. That's convergence. Now, yeah, the only thing I kind of say about that definition is, again, this is important for analysis. This is important for making arguments, okay? If I wanted to prove those theorems that I previously put up here, then I would need to basically go back to appeal to this definition, appeal to things that followed from this definition in order to really see why all of those theorems work, okay? And again, that class is either called something like advanced calculus or it's called mathematical analysis. The point is that is the logical underpinnings for why all of the computational calculus works. It's really important, obviously, for that subject area. I'm not going to ask you to use the definition of the limit of a sequence to prove facts in this course. As we do go through chapter 10, we will focus more on making good arguments for why things happen, but we're not going to get to the point where I'm going to expect you to write high-level math logical proofs. Okay. It is one of the things that makes this Calc 2 harder than Calc 1. Like when people say Calc 2 is harder than Calc 1, they're more or less kind of talking about this, is that you get a little bit more into, but now you have to tell me why you think a claim is true instead of just compute and find a number for a thing. Okay. And use that to answer the question. All right. So I hope that that's a good start to sequences. We're going to use sequences as we move throughout and talk about series for the rest of the chapter.